Hello, Calculus, and welcome to 6.6 Differential Linear Equations, or Linear Approximations. And what this chapter is about, or section, is small differences. It usually, like in life, is what your margin of error is a lot of times. So we're going to learn how to calculate this. You're going to need your calculator, and make sure on 6.6. Let's go. All right, so we're going to calculate differentials. We're going to calculate linear approximations. And we're going to apply this to marginal analysis and error estimation. So right here, these are things that you know. You know that the dy over dx is the change in y over change in x. In other words, this is slope. And we've been doing that for a while. Now, let's just think about this. So I know that the derivative is equal to the change in y over the change in x, because it always finds the slope of the tangent, correct? We know this. Whoops. I think this has jumped every time. So we know that this here finds the slope y. Oh, here, maybe this isn't on. Let's try it again. Okay, let's try again. Slope, there we go. Slope of the tangent. Any place on the curve. We have been doing that now for a while. Now what we're doing here is a differential. So when we actually solve this, so we got dy over dx, so you know this, equals your derivative. I want to find just the change in y. So if I know how x changes, how do I know how y changes? So I want to find part of that slope. So we multiply both sides by the difference in x, and we get this, which is the differential. How is y changing if I know how x is changing? So let's go through here. Get rid of some of this so we can read a little better. So we have y equals 6x squared. I want to solve for dy. Your first step is you know the derivative. So the derivative of y with respect to x is 12x. If I want to know how y is changing with respect to x, I multiply both sides by dx, and this will give me the change in y. Okay, nothing too earth-shattering, right? Okay, let's try this. Y equals 8x to the negative 3/4 when x equals 16 and the change in x is 0.01. So I want to know when x is 16 and it can be off by 0.01, how much will my y be off by? That's what you're looking for. So first we do our derivative. So we multiply, subtract 1. We're going to simplify this, and this is the derivative. Multiply both sides by dx. Now we just plug in our 16 for our x and our 0.01. Oh, that's only supposed to be one decimal for my dx. And this says if x is off by a positive 0.01, then my y is going to decrease by 0.046875 when I go from 16 to 16.01. So at 16, I will be off by this on my y value. That's how much I will lose. Good or bad? Who knows? All right, I want you to pause and try yours. So step 1, you should have found the derivative, which gave you, here, we'll even write it out, 300 times negative 2/3 x to the negative 5/3. All right, simplify that and multiply by dx. So I'm going to move this guy up and here. So now dy equals negative 200x to the negative 5/3 times dx. Now I'm looking for the change in y when x is 8, and my change in x can be off by 0.05. So now we go and we plug those numbers in, and we've got, so that means my y is going to change by, negative 200 times 8 to the negative 5/3 times 0.05. Type that in your calculator, and you should get a negative 0.3125. So this means if x, it's hard to write today, is off by 0.05, then y decreases, so I'm losing again, 0.3125. That makes more sense when we put it into story problems. All right, now a linear approximation. We're showing you this here because it's actually a branch of mathematics. You can make a lot of money if you're good at it and if you like it. It's probably not one of my favorites, but that's all right. So we're going through here and let f be a function whose derivative exists for non-small values of change in x. So I have a derivative and I have a change, or I have a differential. Okay, we know dy is close to the change in y. So let's just walk through this. F of x plus the change in x. So remember when we did x, or like 1 plus x, and then we did it as x approached 0? That's kind of where we're at here. So this is the function of x plus the function of the change in x. Well, we know that the function of the change in x is technically the change in y, right? So what is, if you read this, so this here is when I give you x, what does y equal? This is when I give you the change in x, what does y equal, or the change in y, which is what we're here. Nothing different. Now we're just going to rewrite the change in y, because I know the change in y is the first derivative times dx. That's what we did above. Nothing too major, right? So that means I take my original function plus the derivative with respect to x, or times the change in x. Now, we're going to use just a straight number, square root of 50. No calculators. Now, square root of 50, we don't know. We can guess, but we don't know. So we choose a number, square root of 50, that has a square root in it. I know 50 is 49 plus 1. Everybody with me so far? So I know the change in x here is 1, because 50 minus 49 is 1. So my change in x, or my d of x, is 1. I have to do the derivative of my original. Well, that means I'm going to take the 50 out and replace it with an x, so I can do this with a variable. Rewrite it with my exponent. Now my derivative is 1/2 x to the negative 1/2. Now we're going to use this function right here, the original plus the derivative times dx. Well, the original is the square root of x. My derivative is 1/2 x to the negative 1/2. And then the change in x. Well, x in our case is 49, so we can put 49 in for x. The change in x is what we found up here. That's our 1. Type that into the calculator, and we get 7.07143. Now, actually type in the square root of 50 in your calculator. You will see they are very, very close. Not exact, but close. Close enough. All right, this in here I wrote wrong. This is supposed to be the cube root of 998. So cross that off, pause, and do that problem. Okay, the first thing you should think of is the cube root of 998. I don't know, but I do know the cube root of 1,000 is equal to 10. So then I know that 998 plus 2 equals 10, or 1,000 minus 2 equals the 998. I have to go down to get there. So f of x, so what is my function truly? So this is where we take out the number and we plug in a variable. So we got the cube root of x, which is x to the 1/3 power, step 1, right? Step 2, what is my derivative? So my derivative is equal to 1/3 x to the negative 2/3. Everybody good there? Now we have to actually find what we're looking for. So to do that, remember this is f times x plus the change in x, which is equal to my original, x to the 1/3, plus my derivative, times d of x. Well, this time, x, my original, is 1,000, and my change is negative 2. So my original, x, equals 1,000, your change in x is -2 because we're going down. Now all you do is you plug that in. 1,000 to the third plus 1/3, 1,000 to the -2/3, all times -2. Type that in and you should get 9.99333. Type in the actual square root. So now you're going back to your calculator and you're going to type in the 998 and you should get 9.993328. Again, very close, but just a little off. I hope you did a good job. Those are kind of fun. All right. We are going to use differentials to estimate cost and find the next unit price. So our first step is I have to give you the cost function. I could make you find it too, but either way, you're starting with the cost function. We're going to do our first derivative. So to approximate the change in C when the change in X, this is very important, change in X is 1 and X is 3. So when I have 3 and X changes by 1, how does my cost change? Step 1, derivative, 6x squared. Okay, now I could do this. So now we're going to plug in 3. We get 54 to estimate the cost. Now the change in cost is C4 minus C3. So we're going to plug this into my original and I get 74. See how they are not close? Okay, so since the derivative does not match this, this is a very poor estimation. We are not happy. Now this is marginal analysis, a little bit different now. Same cost with 50. So we do the same derivative. We plug in 50 and we get 15,000. All right, when we plug in 15,000, let's do the 51 and the 50, we get 15,302. Estimation is good, so not too bad. We're not too far off. Remember now that our change was 1, so nothing is too major here. Okay, I want you to pause and try yours. Okay, I put in natural log to see if you remembered how to do this derivative, because that is important. Upcoming sales should be as much as 10,000 phones. Okay, I did not write this right. Could be high. They're off, so it's high, so it's a positive value by 1,000 phones. Approximately how far off his profit estimation will be. So step 1 was your derivative, and you should have gotten 4,000 over x. Remember the derivative of the natural log is x times the change in x. I hope you did well there. Now this time when we do, we're going to plug everything in. All right, x is 1,000. And my change in x is a negative 1,000. Because he's off, he's high, right? So that means he needs to lower it by 1,000. So when you get this, he's going to be off by $400. So he's $400 too high for his profit. Not terrible. Could be worse. Okay, now let's do actual. So now you're doing the actual. How much did he really have here? And we'll have 4,000 times the natural log of the 9,000 plus 4,000 times the natural log of the 10,000, because remember we're too high by 1,000, so we went from 9,000 to 10,000. And when you plug that in, you're going to get negative 421. So we're only off by $21. So his approximation is not terrible. All right, try this and see how you do with this. Okay, ball bearings must be made with a radius of 1.25, an error in the radius. Okay, so we have the radius equals 1.25. Error in the radius, so the change in the radius is what we're looking at, is 0.025. That's from our reading. This is what we know. Estimate the maximum error in the volume of the bearing, so volume. So we know volume is equal to 4/3 pi r cubed. And we want to find the error in volume. So what we have to do is do our first derivative. So the first derivative volume. Now this here's just a number, right? So you multiply by 3. So we get 4 pi r squared times the error. Now we just plug in our things. So the change in the volume is equal to 4 pi, r is 1.25, and my change in r is 0.025. Plug that in your calculator and your volume could be off by 0.4909. Let's look here, and we had millimeters, so volume is millimeters cubed. I hope you do a great job. Make sure you post questions.